Okay, so in this video, we will determine whether the series converges or diverges with the comparison test. As we are summing, and we'll see when we expand the first few terms, positive terms. So at least we can attempt to use the comparison test. So the first term when n equals 2, if you plug it in, you will get 9 over 23 plus the next term when n equals 3, you'll get, if you plug it in, 28 over 87, and so forth. So we have a series of positive terms. We can attempt to use the comparison test. Now if you look at the sequence, there is nothing geometric about this sequence. There is no exponential function. All we have are powers of n. So if we are going to compare this series with a series that we know enough about, which usually will be a p-series or a geometric series, well, here it's going to have to be a p-series. The question, of course, is, do we bound this series above by a p-series or below? And we have to be careful, because this will depend on whether or not we believe the series to converge or diverge. Well, let's get some intuition. As we've said many times in the past, when we try and figure out whether a series converges or diverges, the first few terms don't matter. So we can drop the first 50 terms, the first million terms, the first billion terms. It doesn't matter. It will not affect convergence. So what we're really saying here is all that matters is what is roughly a n when n is large. Well, let's see if we can have some intuition. The dominant term on top is clearly n cubed. When n is large, n cubed is way bigger than 1. And on the denominator, when n is large, n to the 4 is way larger than n and 9. So we single out the dominant term on top and on the bottom. If we do simplify, we're left with 1 over n. And this is now a simple expression, 1 over n. If we sum over these terms, then this will be a p-series with p equals 1, which we know diverges. This is the classic harmonic series. As we're summing over 1 over n from 2 to infinity, this will return infinity. So this is the intuition. So we have our original series, an, but we're saying when n is large, an is roughly 1 over n, so summing an should be approximately summing 1 over n, and as we've just said here, we have a p-series with p equals 1, which is less than or equal to 1. We only have convergence when p is strictly larger than 1. So if you write this out, you'd have 1/2 plus 1/3 plus 1 over 4, dot dot dot. As we have a divergent p-series, we are summing positive terms. The result diverges, so it has to diverge by blowing up to infinity. So the intuition suggests that the original series should diverge by blowing up to infinity. So now, what we want is to show that this series is at least as big as infinity. So we want to bound an below. So let's see if we can do that. So an is n cubed plus 1 over n to the 4 minus n plus 9. So we want to bound an below by something that will roughly be 1 over n. Well, let's look at the numerator. If we drop the plus 1, then we're making our numerator smaller, so the whole fraction will be smaller than the original fraction. So this is clearly true. Well, this is as simple as it's going to get. Let's now look to clean up our denominator. Well, if you look here, we have n to the 4 plus 9. And I'll just reorder these terms. So I have n to the 4 plus 9 minus n. So we have this term minus n. If I drop the minus n, then this becomes bigger, as I no longer subtract negative n. So if I drop the negative n, this becomes larger, but if we divide by something larger, the expression becomes smaller. So this fraction is smaller than this fraction, as we have a larger, clearly, denominator. So we're almost there. We're almost at n cubed over n to the 4. The only problem is the 9. And here there is a twist. If you want to drop the 9, think about what happens. If you drop the 9, then you make your denominator smaller. But if you divide by something smaller, it will become bigger. So here you'll have the inequality in the wrong direction. And this will completely destroy your argument. So the question is then, if we cannot drop the 9, what do we do with it? Well, let's go back and look at our lower bound of summation. N begins at 2. So n is 2, then 3, then 4, and so forth. So n is at least as big as 2. So we know this. And what do we want to end with? We want to end with an n to the 4, as the intuition suggested. Well, if n is at least 2, take the fourth power on both sides, so n to the 4 is at least 2 to the 4, which is 16, and 16 is clearly larger than 9. And so you see, because of our range of summation, n to the 4 is strictly larger than 9. And this is now the key to having the inequality in the right direction. If I replace 9 by n to the 4, then I replace 9 by something that is larger, so I have a larger denominator, therefore a smaller fraction. So now we have the inequality in the right direction. And again, n to the 4 plus n to the 4 is larger than n to the 4 plus 9, as n to the 4 is strictly larger than 9. But if we divide by something larger, the new fraction becomes smaller than the old fraction. And this is exactly what we want, because we're left with n cubed over, well, n to the 4 plus itself is 2n to the 4, and we can simplify. This is 1/2 times n cubed over n to the 4 is 1 over n. And now we have our bn, which is a little off than what we initially had from the intuition, right? We said that bn should roughly be 1 over n, but now we have that bn is 1/2 times 1 over n. But 1/2 is nothing but a constant multiple, so it doesn't matter. So now we're good to go. We are saying that an is bigger than 1/2 times 1 over n. Therefore, if we sum the larger terms, this will be at least as summing up the smaller terms. Well, we can do two things here. First, let's rewrite what bn is explicitly. 1/2 times 1 over n. And 1/2 is a constant multiple with respect to n, so we can factor it outside of our series. So we have 1/2 times the sum from 2 to infinity of 1 over n. But we've already discussed this previously in our intuition. If you're summing from 2 to infinity 1 over n, this is a divergent p-series, therefore it blows up to infinity. So this is 1/2 times infinity, which of course is infinity. So now look at this. The initial series is at least as big as infinity. Well, the only option is that this series is infinite as well. If a series is infinite, of course it diverges. By, of course, a comparison test. So we can go back to the beginning and state our conclusion. So the series of an So 9 over 23 plus 28 over 87. So if you try to add all of these terms, in the end, the sum will become larger and larger out of bounds, so it will blow up to infinity, and this was by the comparison test. And that's it.